Fabulous. Well, thanks so much for coming. I'm really happy to have Jonathan Protzenko visiting today. He's worked on many Galois-related topics, including theorem proving, verified cryptography, high assurance parsing, and also some topics which I guess you won't talk about, but he's also more recently been doing stuff on the law and kind of like capturing the law in DSLs. So a bunch of super fascinating stuff. So I'm very excited to see what he talks about today. Go ahead.
Thanks, Mike, for the introduction. Pleasure to be here. What I thought I would do today is basically recap the past several years of a journey through verified protocol stacks that includes the cryptography, protocol, and everything in between. So we're going to hear about many projects that I've been a part of over the past few years.
Is everything our screen? Just trying to get rid of the thing on the screen.
Leave meeting.
Leave meeting.
Science.
So you're going to hear about projects like Hacklestar, Evercrypt, BitSignal, Noistar, and many more. This is, and I want to emphasize that, of course, a joint effort with many other people, several of which are in Microsoft Research, some others are at INRIA in Paris, some were at CMU, Edinburgh, and it's been going on since 2016. So this is, of course, the work of many different people. Essentially, the Everest project was about establishing a fully verified protocol stack for the HTTPS ecosystem. I thought I would spare you with the usual motivation slides because I'm sure you're all pretty much convinced here that there are many problems with secure communications, implementation bugs, broken cryptography, buffer overflows. So the idea was to try to replace every single component of that stack. And so we started at the bottom, starting from the cryptographic algorithms, the Hacklestar and VeilCrypt libraries. We moved on to more abstract libraries such as Evercrypt. In parallel, we were working on parsing and having verified secure parsers. And then over the past couple of years, we have been slowly moving up the stack. We have been looking at protocols and even high-level libraries with state machine and high-level APIs. And so the way that I've structured, well, I should, of course, do the obligatory slide to say that a lot of these components have been deployed and adopted in various products. Our big champion is Firefox. NSS thought that it would be better to have verified cryptography once and for all. And I think by now, almost half of their algorithms are straight copy-pasted from our repositories. Another one of our big champions is the Tezos blockchain. They think it's really important to be state-of-the-art in terms of security. And they have been big sponsors, both in terms of publicity, financially, and like sponsoring students, and the part at INRIA especially. We have one of our algorithms that has made it into Linux. It was Jason Donnenfeld when he landed his crypto library for WireGuard, the VPN. ARM Embed used some of our stuff a while ago, and I think talks have restarted to use more of our stuff. And at Microsoft, we've had some amount of success with some projects. What I thought I would do is give you a tour of all of the various projects, kind of recapping historically how we went from just one little crypto algorithm to a complete protocol stack. And also because we're at Galois and I know that everyone is quite engineering focused, I thought I would talk as well about the infrastructure that's behind the scenes and all of the engineering and the careful craftsmanship that it took to keep it all together. And at the end, I will talk a little bit about what I think is the future of verification toolchains. Part one is a tour of the verified stack. And I finally figured out what the point of Dolev-Yao is. It's to generate images for my talks. So this one, I think, is Tour de France in the style of Chagall or something. We're ready to embark on a journey through verified code. So you are here. This is where we started in 2016. And essentially what we set out to do is start with the core cryptographic algorithms. And so there was a lot of joint development that happened between MSR and INRIA. At INRIA, they were focusing more on the applications, which is the Hacklestar cryptographic library. And the idea was to take modern primitives that didn't have really compelling implementations or maybe were better crafted and were easier to implement. That means things like Chachapali, things like Curve to 5519 or AD to 5519. And what we did was we produced C code so that it could be integrated with an existing software ecosystems. And that was a very important point. We wanted to be very realistic and meet people where they were. And giving C code, It's not the most exciting from a theoretical perspective, because I think a lot of people have strong feelings about C for very good reasons, but the goal was to give verified crypto, and that was the way to do it. And concurrently, what we did in terms of toolchain was develop the low star toolchain. For that, we use the F-star theorem prover. It's a dependently typed programming language that allows you to write code and prove properties about that code. And what we established was a subset of F-star that models C. It models structs, it models machine integers, it models reasonable memory management. It doesn't model all of C, but it models enough to write crypto primitives. And with that, along with a few libraries that model what it means to have an unsigned 32-bit integer, arrays, or what it means to have allocations in the stack and the heap, well, together that gave us a toolchain that would take programs written in that subset of F-star and compile them to C. The tool was called originally Kremlin. It was a pun on KNR meets ML, but it stopped being funny quite fast, actually. So now it's called Caramel. And it's a compiler that goes from low star to C and gives you very idiomatic readable C code that you can trust and drop into your C code repository. I'm just going to give you an example. It's a very sophisticated function that multiplies by 9. But here's the low star implementation. You do a left shift by 3 places, and then you do A plus B. And the idea is that you're going to decorate this low-level, efficient implementation with a specification. Your specification is going to say that your result is 9 times the input. And that should be really, really familiar to all of you here. If you're trying to verify this using the F-star theorem prover, it's going to complain, and it's going to say that you're missing actually a crucial fact to show that the result is always correct. And that crucial fact is given by Z3, the SMT solver, which tries to solve the proof obligation and comes back and says, well, actually, you need to show that your result fits in a UN32, otherwise you cannot always unconditionally prove that this is a multiplication by 9. So in blue, you have low star code, which is low level, efficient, and compiles to C. And in green, you have specifications. Specifications are entirely static. They're not checked at runtime. You don't have any extra burden from those green parts, meaning that you can run this code through the Caramel compiler, which will give you an efficient C implementation that looks like your original C code, except that the original low star code, except it's now C code. Yes, I should say, by the way, I forgot to say, I'm happy to take questions.
Okay. I was wondering, like in your specification, so the types kind of don't match. So I'm assuming that there's some kind of mapping between UN32
Yes,
and integer.
It's much more verbose in practice. Usually there's what you call a V function, a value that allows you to reflect a low-level concept such as a machine integer as a pure type. For instance, a natural number. Same thing with an array, right? You have a function that takes a given state of the program and the low-level array and reflects this as a sequence for the purposes of specification.
So did I hear you right that this is morally right, but it's not literal?
It's not literal. I'll show in a couple of slides like actual code, but then everyone will be scared. So, okay, this one is more literal. This one is exactly the same idea, but with a slightly more realistic example, the Poly105 message authentication code. You have a destination parameter that is an array of 16 bytes. You have a length, you have your message, you have your key, you have preconditions about how these arrays have to be disjoint in memory. You have another precondition here that says that they all have to be live. So they have to be valid pointers in the input heap H. And then C here, it's stateful verification. So in the style of Daphne or for instance, you're going to relate the input heap and the output heap by saying that going from the input heap H0 to the output heap H1, the only thing that gets modified is your output parameter, the tag. Furthermore, the value to be found after the function has been called exactly matches the specification. So this is kind of a more involved example that puts together all of these concepts, but for an actual cryptographic algorithm. And same deal, you feed it to the dedicated compiler and you get very readable C code. And so that's the essence of our toolchain and our methodology. And one great thing about it is that, you see this code and you're like, wow, this is a really gnarly low-level implementation that does a lot of very specific things with like maxed equalities and a lot of lemmas for doing the proof that you're computing the right thing, but you actually don't have to trust any of that actual code. All that you have to trust is that your specification is correct. And a specification is usually pretty concise. It's pretty minimalistic. You audit it, you test it exhaustively, and in the end, you end up with a proof that your low-level specification matches the implementation. That means that you have functional correctness. That also means that you have memory safety by construction. You have to prove memory safety to show that you get the right result. And then we also have, and that is for the crypto specifically, we have proofs of side channel resistance, the most basic form, meaning that you cannot use secrets to do tests, which would be timing leaks, or to access memory, which would be memory leaks. A word on the compiler. I know this is a topic that interests a lot of people. I know the Amazon folks are also very interested in generating idiomatic code. There's been a lot of work on generating clean, trustworthy code from the original proof. And that is important because otherwise people don't think you're serious. If you have unused variables all over the place or ugly auto-generated names, it doesn't matter that the code is auto-generated. They don't take you seriously from an engineering perspective. And so there's a lot of stuff that went to the compiler, both in terms of programmer productivity, decompiling like high-level data types into a series of if-then else's or monomorphization, just so that you can be more productive in the source while relying on the compiler to simplify the work for you. But there's also like a plethora of tiny little things for code quality, such as removing all of the unused arguments, doing little people optimizations, all of which gives you code that is very idiomatic and that people feel comfortable dropping into their source repository. It's about 20,000 lines of OCaml, and it's really the workhorse compiler of that entire toolchain. The next thing we did after establishing that toolchain and establishing the idea is to rewrite everything. I'll talk more about that in the second half of the talk, but there really is a lot of work to do to have robust proofs and something that can scale from an engineering perspective, and we did not have it in the V1. I'll talk in my second part of the talk, the behind the scenes look, a little bit more about what it took, but I would say that the V2 of the Hackle library was a more complete, smarter rewrite. And there was both work on the underlying libraries, having really efficient libraries to model arrays and memory reasoning and really honing the way that you would send these to the SMT solver. But there was also a lot of PL-based techniques. So we have come to rely a lot on partial evaluation and meta-compiler, meta-time programming. The idea is that you can write a lot of code that is not technically low star, code that is very generic over the flavor of algorithm or your choice of representation. But you can rely on the compiler to specialize it ahead of time and do a lot of beta reductions and compile time evaluations that will eventually give you code that fits within the low star subset. I have an example on the next slide, but if some of you are familiar with, say, hash functions, which have an init, update, finish kind of decomposition, you don't have to write the function that combines the three of them every single time. You can write a generic hash function that says, give me an init, update, finish algorithm. I will take care of the chunking, plugging these things together, and I will give you a specialized hash function for this choice of init, update, finish. And that is great because you write your hash function once, but you specialize it multiple times for all of the SHA-2 variants or SHA-3 or something, and you end up with very generic programming. It's almost like templates on steroids. And we used that kind of technique pervasively through the rewrite, which significantly decreased the effort and allowed us to really have a great proof to code ratio, by which I mean that we write a little bit of proof and get a lot of code out.
So you mentioned on the previous slide that it's very important that you generate pretty C because people don't take you seriously otherwise. So does that mean that, because I was picturing when you said it's a library, I get a library, I link him with it, and I usually don't look at the assembly. So do people actually get the generated code? Yes. And they commit and so if anything needs to be changed,
they come to me.
Don't do that.
Yeah, so here's the workflow. We produce C code under version control as part of our repository. So we do the low star to C translation, and we have the C code under version control, and it's refreshed every night so that if we change the proofs, there's a corresponding change in the C code. And then people just take the subset of algorithms that they care about, drop it into their source tree, and don't touch it because they want to be able to refresh it from upstream. Some people call it vendoring a library. And
did you say vendoring?
Vendoring. They call it vendoring a library. I was submitting a PR on Python a couple of weeks ago to use verified crypto, and they call it vendoring. They have entry copies of existing libraries that they prefer to keep as part of their source code, rather than having to deal with someone else's build system dependencies and linking together.
Okay, and so to know that it does the right thing, they, instead of looking at the specification, they actually look at the generated code.
Yes, that drives us nuts. But the reality has been that people are like, yeah, you're researchers, but I want to see some C code. And one anecdote that I almost always tell is that when I wrote the Caramel compiler, I took the C grammar and I wrote a pretty printer for arithmetic expressions that was following the C grammar and inserting parentheses whenever necessary. And the Mozilla guys came back screaming, like, you're triggering all of our compiler warnings. No one knows the relative precedence of left shift and plus. Are you crazy? And so their main feature was more parentheses so that they wouldn't have compiler warnings. Or I was like so proud of my little like super precise name resolution mechanism that would know exactly when it was okay to shadow a variable. Of course, their compilers were like not happy. They were like, no, you're shadowing variables in C. You're going to shoot yourself in the foot. Don't do that. So there was a lot of that had to be incorporated. Yep.
Are you verifying the meta, the generic program? So you had to use it like this template on steroids, and then you generate the low star. So are you doing the property verification on the
We do it
generated?
within F-star, and we rely on the correctness of the reduction facilities of F-star at compile time. So the reduction machinery of the dependently typed programming language. Here's an example. I'm using the hashes as an example because it's representative, but it's not too complicated. Many hashes have a core compression function. And what you want to do is if you're writing SHA, for instance, the compression function is the same for all 4 variants of SHA-2, except that some of the constants change. Or maybe the internal state type is changing because it's either an array of 32-bit integers or an array of 64-bit integers. What you want to do is write a single compression function, not 4 copies of it, because that would not be very productive. However, the type state here, it's not a low-level type. If you were to compile this straight to C, it would be maybe an untagged union that's either a 32-bit or a 64-bit integer, and that would take up too much space for SHA-256. People would say, you're crazy, this is terrible C code. But what you can do instead is partially apply compress to a specific choice of SHA-2 algorithm, and at compilation time, everything will reduce in the dependently typed theorem prover and will give you a specialized version of SHA-2 where the type state A becomes state SHA-256, which in turn becomes array of 32-bit integers, and you've managed to write 1 compression function but get 4 for free. And yep.
So that makes sense. But do you know that, how do you know that that will happen, right? So you kind of hope that the compiler does that, and it's always very hard when things are magical like that and not explicit.
Of course, I'm showing a simplified version. There's a series of attributes that allow you to specify precisely what is expected to reduce at compile time or not. And there's also metaprogramming facilities that allow you to script the compiler if that's not enough, where you can say, I'm going to drop into an interactive mode where I can say, unfold this definition, that one and that one, reduce this, reduce primitive operators, and then you get the code that you want. Another thing we did after that was go for more high-level APIs, and that project was called Everest. The idea was that sometimes you do want some parts of your code to be written in assembly, and for that we relied on a technology called Veil, which is a deep embedding of x64 assembly and semantics in F-star. And we were able to combine the two, by which I mean that, say you have an implementation of curve 25519, maybe your core big num operations are written in assembly to be really fast, but the other parts, like the letters, are written in low star just so that you're more productive and don't have to write the whole thing in assembly. We have a single specification result by which we state that regardless of whether you're using assembly or a pure C fallback implementation, you get the same result. And the library comes with automatic CPU detection and multiplexing. So it will probe your CPU for you, and it will provably choose an implementation for which you have shown that you have the right CPU flags. So that's a cool result. You're never going to get an error when you invoke, say, an AVX2 implementation without checking that you do have the AVX2 flags before. Another thing that was more high level was kind of offering more abstract APIs. You don't want to offer like 12 hash algorithms that all do the same thing. You want a single API where you say, instantiate a hash state, a digest state for this choice of algorithm, and then you want to hide all of these like choices of algorithms underneath the hood. And that we call agility, and that was a big component too for factoring out the proofs, having very tight, compact, sealed interfaces, which was really foundational to allow further applications to be built. You don't want to have a big context. You want to have very abstract, sealed specifications. And of course, we wrote a lot more algorithms. Just to make ideas really clear about what the toolchain does, I have a little animated slide here that I thought you might enjoy. Starting from the specification, you write something very concise. That is your spec. This one is for GF128, the Mac that is used, the field that is used for the Mac of GCM. And so this would be your specification. It's super concise. It's math-based. You can read it. It's 8 lines, and you can convince yourself that you truly have defined modular reduction in that field. You test that. You can extract it to a camel. It's not very efficient. It's not intended to be run in the real world, but you can still extract your specification and run it at some test vectors so that you have confidence that you're about to prove the right result. The next thing you do is that you can do another step where you get a little more concrete. For instance, you might want to start introducing a choice of representation. You might start talking about left shifts or maybe masking equalities that are not leaking any side channel information. That is still not low start code. It still doesn't go to C, but at least it's an intermediary step that talks about more of the implementation details.
And this one's written by hand.
Yes, it's also written by hand because you want,
Of course.
you want your algorithm to be like that. And then you can do your low-level implementation. And of course, you're going to show it against the mid-level spec. Either you do it in Veil, where you have that DS cell that allows you, there's a little bit of a front end that allows you to write assembly code and then send it into FStar. Or you can write it in low star like we talked about before, and then that's where you talk about the stack effect, your buffers have to be live, you modify this memory location, here you're doing a loop, and so on. The Veil code can be printed into assembly. The C code is running through the Caramel compiler into C code, and then you can combine the two and link them, and you get a library. The one thing I have to say, and I won't hammer it throughout the talk, but we are fast and actually sometimes faster than the competition. For the specific Evercrypt paper, we exhibited one machine and one configuration for which we were, I think, just a hair faster than OpenSSL. So my message here, and it's valid for the entire talk, is you don't have to choose between speed and verification. You can get both. Whether you want to beat OpenSSL or not is your choice. It might require more effort. You might have to drop into the assembly subset if that's something you really care about, but it can be done. Yep.
That because you guys are really good, or is your tool chain optimized in some interesting way? Like you just happened to implement it in an efficient way? Like
We took most of the OpenSSL optimizations because they have that great guy called Andy Poliakoff who loves to optimize every single algorithm as much as possible. And then we did some fine tuning for pipelining for the one micro-stepping architecture that we had. And that was mostly Chris Hoppitzel's work, and he's really good at that. So he found one kind of slight rewrite that would allow to do more intermediary computations more efficiently. That basically took us over the edge. But you see, it's not a huge difference. It's maybe 2% or something really small.
So presumably somewhere you had to encode the whole binary sort of interface of how C calls functions, because it's different on different machines, I guess. So presumably that's part of Veil. And then is there some verification that the assembly sort of doesn't mess up your C state kind of?
There's a connection between the memory models of assembly and C that shows that once you jump into the assembly, you have to show that you don't touch any other memory beyond what you get as your parameters.
Okay, so you just give.
And then you know that the assembly doesn't get your C data structures shut. And there's a stitching of the two memory models, the structured memory model of C with pointers. Is pipelining done manually in the Veil code, or is there automation surrounding that? Yeah, the Veil folks had a paper at a workshop where they started doing automatic transformers for assembly code that were correct by construction and would allow them to explore more rewritings for different pipelining strategies. Great question.
The Veil code you showed was very x86 specific looking.
Yes.
Most people carry on ARM devices these days. I'm sure your users have talked about it.
We're at a stage where we're mostly waiting for someone to say, yeah, I will really use your code if you give me ARM. I think it's not too hard to add a backend. What you want to do is have the taint analysis also replicated to make sure that you don't leak any information. Veil has its own taint analysis mechanism that's different from the Lodestar one. So if you wanted a complete ARM backend, you have to revive the early experiment and do proper taint tracking, and then you'd be in business. Yeah.
So when you're saying you're applying all the OpenSSL optimizations, can I think about that code as being more or less the same as the OpenSSL code, or is it, do you need to write it in a different way if it in the assembly level to fit with the way that the verification works, for example?
It's not, usually we don't look at very large chunks of assembly code. So if you have your loop invariants, Veil is slightly above assembly. It has a like structured loop construct so that you can have an invariant. So maybe you would introduce that and the invariant, but it's not excessive. For C, on the other hand, we have almost always found that we need to slice up the C code into smaller functions that each can be proven individually with crisp pre and post conditions. We of course rely on like inlining and partial evaluation to stitch all of these back together, but for the purposes of verification, the C code is the one that you need to like slice really thinly to make sure you have a happy time verifying it. You can always roll up your sleeves and verify a big function, but you're not going to be very happy. All right. One last thing that I will mention is that we're capable of dealing with like more subtle APIs, and that's what we were talking about over lunch, the ones where you can feed data byte by byte and have an internal buffer that is progressively filled with data. And these incremental APIs are the one that you find in the real world and the ones for which there was a CVE in Python just a few weeks ago for SHA-3. And so this was a very fun piece of PL-oriented work where we took all of the partial evaluation tricks and actually, I wrote a functor that takes any block algorithm and gives you a bufferized version of it that has all of the internal buffer. And that was exactly kind of the philosophy that I advocate, where you write a piece of code once that transforms a block-based algorithm into a safe one with a foolproof state machine that relies on an internal buffer. And we applied it, I think, 8 or 10 times to all of the hashes, Blake2, which is a keyed hash, Poly1305, which is a MAC. And that kind of automated large-scale code rewriting gives you really a lot of bang for your buck. This one is, I think, for one choice of algorithm, for 1,500 lines of Lodestar code, we ended up with 6,000 lines of C code. So it's great, you write it once and then you reuse it a lot of times. It's like a super advanced template. But that was all like very fun and great, but the interesting bit is actually moving beyond the crypto algorithms, starting to think about what we can do about protocols. And that's also something that was a big area of focus. And there were a couple early works about protocols. The first one was Signal, a verified implementation of the Signal protocol, which is used for like secure communications on WhatsApp or Facebook Messenger. And that was essentially the core transitions of the protocol. Maybe do a round of ratcheting or something. All these functions were individually verified on Lodestar and actually extracted to the WebAssembly backend of Caramel. But the proof of security was kind of done using another tool, ProVerif, which wasn't completely satisfying. It wasn't like an end-to-end proof. There was another attempt in 21, and I wrote a lot of that proof. It was a security proof in the game-based style. It was used for BTLS, and it was for the record layer of the Quick protocol, which is the successor to TLS 1.3. And it was getting better, but it still didn't have kind of the complete protocol stack aspect that I think we really were after. And so that came when we started looking at the noise protocol. So allow me to tell you a little bit about the noise protocol, because that's a really cool piece of work that we talked about this year at the Security and Privacy Conference that I'm actually feeling quite excited about. Some of you may be familiar with noise. It's a little domain-specific language of key exchange protocols between two parties. It's essentially the space of all of the handshake protocols you can have when you have a Diffie-Hellman, a key derivation function, and symmetric encryption, of course. And so I'm not going to go into the detail of what these little things mean, but for instance, when you see like E, it means generate an ephemeral, do a Diffie-Hellman with the other party's static key, then encrypt everything from here on using that key, and then send your static key to the other party, and then do another Diffie-Hellman between the two parties' static keys, and then that will be your encryption key for the rest of the data. It's a very compact encoding. It's actually used in a variety of scenarios. One-way encryption, authenticated server, and it's used by actual applications. IK is one part of the WhatsApp protocol. IK PSK2 is used in the WireGuard VPN. And Well, what can you say about the security of these protocols? Yeah.
I'm finding it a little tricky to read this, I mean, to parse it. Could you walk us through it again as to,
Yep.
I can intuit what the left and right arrows mean, kind of, except I don't know, like I'm sending a secret or receiving a secret, presumably, but I don't know if that's an encrypted secret or not an encrypted.
So it's a very compact encoding. So let's look at this one. Initiator is on the left, responder is on the right. Everything above the dotted line is out of band material. So the initiator starts with the other parties, the responders, public static key. So here, because you have the public static key.
How do I know it's a public static key?
It's an implicit fact of the encoding.
Okay,
It's a very compact encoding. So
Sure,
it means
sure.
that from this point on, you're encoding with that key. You generate your ephemeral, so the initiator's ephemeral key. Diffie-Hellman with the responder's public static key. Send that shared secret over. You have the shared secret, so you can use that as your new encryption, symmetric encryption key with a key derivation. Then you send over your own static public key. Both parties do a Diffie-Hellman between their respective static keys, and they have a new shared secret from which you can derive the encryption key, the symmetric encryption key.
so I mean, what I hear you telling me is this is what's going on at each of these steps, but I don't see any way to tie that to, like, are you saying that whenever I put two letters together, that's Diffie-Hellman encryption?
Yeah.
Okay, so I guess it's that kind of insights that I'm looking for.
Yeah.
As opposed to what a particular one means. So on the next line, you've got three things together. No, I'm sorry, the next one to your right.
Yeah.
You've got three things together. Is that a Diffie-Hellman of those three things?
So that's a PSK, that's a pre-shared key.
So I guess I'm still trying to get a little intuition as to the notation, as to how I should interpret things in the notation.
So you should interpret two letters as a Diffie-Hellman between an ephemeral and a static, or a static and static, or an ephemeral and an ephemeral.
Okay.
And PSK is, well, it's a pre-shared key.
And is there any difference between SE and ES?
Yes. ES means initiator's ephemeral on the left and responder's static on the right. And SE means
Yeah, the other way around.
initiator, yeah, the other way around.
Okay. So it's a sort of non-compositional notation. I mean, okay, right.
It allows you to express about 59 protocols that each have different security properties. The key question here is, what are the security guarantees you get at this stage? And how can you express them? And
Okay, thanks.
Yeah, thanks for the question. And they're quite used, actually. It was designed by Trevor Perrin, the guy who was initially working on the Signal protocol, because he wanted to have a more generic framework to express these things than Signal. And so the reason I'm excited about this work is that it reuses a lot of ideas that I've talked about, namely the idea that you want to write one version once and for all for any one of these 59 protocols, but then get 59 specialized implementations for free. So I'm not going to go into the details of this because it could be an entire talk of its own. But what is interesting is that in this piece of work, we finally get beyond just the crypto algorithms. And we started looking at what it takes to have a complete protocol implementation. So by that, I mean, for instance, that there's key management. In some scenarios, you want to keep a database of the clients who are allowed to authenticate with you, and you identify them through their public key or the hash of their public key. And that for that, you need a data structure that allows you to index. So we started writing some data structures in those star, like imperative maps that allow you to map a public key to an identity. And if you keep going up the stack, you need a state machine, one that is capable of moving you through the steps of any protocol and advancing you through it, and refusing to move forward if, for instance, there's a key mismatch or you can't decrypt something. And you want the state machine to be foolproof. That is, if the state machine goes into an error state, you want to be stuck there, and you don't want to have static checks, you want to have dynamic checks. And on top of that, you want a friendly user API that has a high level concept of, I want to send this message at this level of security, and the API must bear out if your chosen protocol is not strong enough to give you that level of security, or if you haven't gone far enough down the protocol to achieve that level of security. And so all of that we did, and we have very many layers of low-star code that essentially build on everything I've talked about before. All of the techniques are taken up to the next level, and that allows us, and I think that's about 60,000 lines of low-star code, that allows us to have one super generic implementation that takes any one of these 59 protocols. You do your partial evaluation magic. There's a lot of like expertise behind the scenes, and then you get pure C code that has your choice of protocol, your choice of algorithms for that protocol, and your choice of implementations for those algorithms.
Do you have a paper that describes all this?
Yeah, it's Oakland this year.
Sorry?
Oakland
Oakland
this year. Yeah, this is this year's Oakland paper. And I'm happy to tell you more about it because, as you can tell, I'm very excited.
Yeah.
Another one of the reasons why I'm happy about this work is that we finally have a proof of security that we can connect to the low-level development. So no more putting ProVerif and F star side by side. We are using a framework as known as DY star, Dolev-Yao star, that allows you to do proofs of security in the symbolic model. And with that, we can prove the security of all of these things. And notably, the central theorem says that if the state machine advances up to the third step of the protocol, then you are indeed attaining the level of security that you think you have in the symbolic model. And so that's kind of the like final achievement that ties everything together. I would be remiss if I didn't mention the parsers. One last box that I want to cover is the parsers. We essentially have a little front-end language that allows you to describe C structs with a little bit of refinements, and then you low-star code that can either validate or serialize any data structure. I'm running kind of short on time, so I'm gonna go over this because I want to focus a little bit and talk about.
I'm sorry, could I just ask a very quick question?
Yeah, of course.
How would you compare what you did here with the Narcissus stuff out of MIT?
Narcissus is more auto-generated, I think. So
Oh, I see, these are handwritten parsers, are they?
their combinators is the same thing. The front end generates combinators that are then partially evaluated and reduced into a low-star parser and serializer.
And does that mean that they're all recursive descent parsers?
No, we don't have recursion to data formats. So it's basically, think about it like the TLS RFC, header-based length encoding, that sort of stuff.
Okay, cool, thanks.
I think you folks are going to be interested in like a little bit of a look at the engineering side of it. I think this prompt was behind the scenes by Edward Munch or something. It was a funny one. If you just look at the Hackle-Star repository, right, that has Hackle-Star and Evergreen, it's 317 minutes to verify the whole thing. But fortunately, if you have enough of a repairable factor, then you can do it in 15 minutes. And that very simple thing took a lot of work to reach the place where developers would be happy and would be productive. So I want to talk a little bit about that, about tooling, collaboration infrastructure, and how to write robust proofs. There are two improvements that I think as a user have been the most transformative for me. The first one is the interactive mode in Emacs. It's not the fancy new purple paper. It's not the new version of the effect system. It's not any of those things. It's just the ability to process code one region at a time and have instant feedback. And that was a big boost to our productivity. And the second one was parallel builds. So I think one of the big lessons for everyone involved was that productivity matters and engineering is not something to be overlooked. And you can have a huge impact if you just like try to keep everyone alive. Another big thing that we invested a ton of efforts on is continuous integration. I think there's a quote from the NumPy SciPy guy that says that every research project that became to be successful was built upon the ashes of someone's academic career or something. And I think there's a little bit of that in that it's really hard to find the motivation when you're a researcher to debug all of these low-level nitty-gritty things. So one non-technical answer that we found and that I invested a lot on is very aggressive CI. Concretely, what we do is that every 6 hours, all of the projects for the Everest universe are re-verified together with the latest version of each project. And if any project breaks another one, that is extremely frowned upon, and there's a big notification that goes out. And that actually changed the world. Everyone started being a lot more productive once we had that in place. There was a little bit of, I know it doesn't sound shocking, but for researchers saying, hey guys, you all need to be on CI and you don't break the CI anymore, that was kind of a cultural change, but we got there and everyone is super happy now because it gives them insurance. You can say, no, I got a green, so you can't blame me.
Can you talk a little bit about that? Because like it's a very nice thing to have, but how do you achieve it? So when you break something else and it's in another project that you don't know anything, or does everybody understand all the projects and they can go fix all of them?
There are distinguished projects and points of contact. Like they know that if someone breaks something in HackerStar, they can either try to fix it, and if it's not trivial or it requires a deeper understanding, they hit me up. And usually I know to redirect it to, or I do it myself.
That's how you organize your kind of the connections between all of them.
Yeah, you have to, yeah. We are very aggressive. One other lesson that we found is that we don't want to pay for the cloud. It's actually super expensive. We just have 2 big machines with 256 gigabytes of RAM in someone's offices, and that's where all of our CI runs. We have processes, we have like a good review culture that took a while to get there, but I think I can confidently say that we really got professional with the HackerStar repository. We have the maintainers team that meets weekly, that reviews issues, make sure that no PR gets stuck forever. And that also has made the whole team more productive. Another big thing we do is that we test the generated C code on, I think, 65 different architectures. You would not believe the corner cases that we hear about. Some people still care about GCC 4.5 or exotic architectures. There was the one version of Xcode that would fail to register allocate, and it was just that one version, like so much stuff. And actually, a startup was created called Crispin, disclaimer, which I am advising, that actually is taking care of that and professionalizing the development and distribution and packaging of all of the crypto libraries. And that also has been a huge gain of productivity. In terms of proofs, I would say that what has been the most transformative for us is being really super unyielding about abstraction. We have not only abstract implementations, your hash function has type, bytes to bytes and computes the right hash, but also abstract specifications. There exists a hash function and it has those properties, but no one needs to know what the definition of the hash function is. And that's really important when you're in the presence of an SMT solver, where by default, all of the definitions in scope get encoded, and the SMT solver might try to use all of these. Like at some point, you hit a wall, you cannot be productive anymore with an SMT solver, so you have to really introduce really super tight abstraction boundaries. You can do it in C2, you can have abstract struct types in C to make sure your clients don't see into your personal data structures, and that has really worked out pretty well for us. We've had some hard-earned lessons. I think Chris Hoplitzel has like the 10 commandments of writing proofs. I don't remember them, but there's like some stuff that people know. Usually non-linear arithmetic with an SMT solver is a bad idea. You're usually happy because your proof goes through and you come back 2 months later, you don't remember why it was supposed to go through and you cannot for the life of you fix it. So people after a while tend to be disciplined and try to avoid these corners. Or if your proof is just taking an insane amount of Z3 time, then maybe you should like diagnose it, do a little bit of profiling and figure out which one is the rogue lemma that will consume all of your Z3 time. People after a while like kind of get over that wall of complexity and are happy to have very detailed proofs rather than relying on sheer luck and whatever Z3's heuristic is at the time. So there's a lot of low-level advice that you can have. Another thing that we've had to have is, no, but things get worse, right? So a lot of problems we had in the beginning was every institution, every student was having their own style. So we got better. We had some libraries and some guides to people write their refinement about the length in a slightly different way. You might end up consuming an inordinate amount of proof effort just because your abstractions are not exactly aligned. So we also get better at it. And we, once again, like try to be very good about having unified specifications that bring everyone under the same umbrella. I've talked about meta programming at length, but it really has allowed us to save a lot of effort. The last looking forward part that I want to talk about, and this one is actual Hopper painting, it's not auto-generated, it's my last one. is how do I see things moving forward? And the short answer is Rust. We spent a huge amount of time on C because I think it's fair to say that in 2015, C was still, the rule of the game, but things have changed. People are convinced that C has problems. People know about undefined behavior. You don't get the kind of disbelief that I used to get 7 years ago when I told them, no, the compiler is going to erase your null check. And people are actually seriously contemplating Rust for very critical, mission critical software. You have Rust in the Linux kernel, right? And people love Rust. Like everyone adores Rust. 7 consecutive years as the most loved programming language. I'll tell you who's at the bottom because I'm sure someone's going to ask. It's MATLAB and COBOL. Everyone likes those. And there was a very natural transition, right? If you think about what is going to be the next generation of verification tools. And the transition was, if you spent so much time fighting for memory proofs, don't want to fight for memory proofs anymore. And Rust has so much discipline baked in that a lot of stuff comes for free. Like rather than fighting with the SFT solver because this pattern about unused memory locations when disjoint 2 is not working, you just want to circumvent the whole thing in one go. You want to focus on the functional nature of the code. And well, the answer is something we call NAS, which is a new verification toolchain developed with my student Sean Ho at INRIA. And the idea is very simple and it holds in one sentence. Safe Rust code is functional. If you don't use interior mutability, then your Rust code with all of its mutable borrows, shared borrows, and all of these things, all of that is purely for optimization. So hint to the compiler that you should pass things by addresses instead of passing them by value. But you're not in the situation where you have uncontrolled aliasing. You know where all of the aliases are. It's enforced by the borrow checker. And that means that you can translate your Rust code as a pure functionally equivalent code. And if you have a pure lambda calculus equivalent of your Rust code, then you can send it to the theorem prover of your choice and be productive in the tool that you know and love. And so, yes.
If you were to take a Sharpie and draw an arrow from wherever these arrows are to assembly, where would that branch off?
Well, you use the Rust compiler, you keep the Rust compiler.
Okay, so it's all the way from the top. You aren't talking about compiling from lean.
You translate your Rust code to a functional equivalent, you
All right.
prove properties about the functional equivalent, and you trust that the Rust compiler is doing the right thing. It's a very pragmatic choice, but you don't, like I was tired of explaining to students that they had to pay a huge proof just to reason about a mutable stack variable. It's not normal. You should not have to talk about a memory location when all you have is a mutable counter on the stack. And with that, you don't have to anymore. We have a generic kind of reinterpretation of what it means to have borrows in Rust. And it has a usefulness beyond just this toolchain. But yeah, this is what we're spending most of our efforts on and what I'm genuinely very excited about. We have an F-star backend, a Coq backend that actually is starting to work, and we have plans for more. There are some limitations, of course, for now. We don't deal with unsafe code, and we don't have support for interior mutability yet, but we have plans to deal with that. And that was ICFP 2022. That was the paper that we presented most recently. And just to give you, and I think I'm about to run out of time, but I'm sure some of you are curious, I'm going to give you a flavor of the translation. This is C on the left. You have a very silly function that, given a Boolean B, returns either X or Y. In C, you don't know anything. X and Y might be aliased for all you know. They might be null, they might be dangling. So if you want to prove anything about this code, you already have to start by rolling out all of these cases and thinking about all of these things. If you have X here, when you get Z, well, there's like all sorts of problems with aliasing. What happens with Rust is that you can reason about it much better. You know that from the signature of the choose function, X and Y are disjoint. They're not aliased, they're not null, and they're valid pointers to mutable 32-bit integers. And so that means that you have exclusive access guaranteed by the lifetime alpha, and that you can leverage all of these pieces of information to have a nice, neat, clean functional translation. I'm going to stop here. I don't want to dive into NAS. I think I'm hitting the 50-minute mark, but I'll just say that for me, I think this is where the future is, especially the part where you can target multiple theorem provers. I don't think you should be like so committed to doing everything in one tool. If you have a collaborator who's a Coq fanatic or someone who's really productive with HOL4, then that's totally fine.
Have you done automatic translation from C to Rust, being able to sort of discharge the things that were obvious and then present to the user the places where the user might need to do work?
We have not.
Okay.
We have not. That would be an interesting thing to look. We're also trying to look at fresher.
Well, I know you have. But, oh. Yeah, I mean, that's something that, these guys have been working on. I mean, but there may be some interesting for collaboration potentials there.
Sounds like we should talk.
You're on the schedule.
Oh, great.
Yeah, so,
Perfect. Yeah, and well, looking ahead, one big thing that I'm personally interested in is MLS, the messaging layer security protocol, which is the successor of Signal, but for group chats. And there's a reference implementation in Rust. So my dream is to connect using that toolchain to reference implementation to improve of security, just like we did for noise in the symbolic model. And I think that's it. Yes. Thank you. $50 minutes, yes.
Is Eddie also on the schedule? Is Eddie also on the schedule?
Yes, yeah.
Okay, just the end was very reminiscent of work Eddie has been doing.
Great. Yeah, there's no relationship. Yeah.
I have a quick reaction. I mean, this is an impressive body of material.
Makes
sense. Yeah. And I don't know, Mike, how hooked in we are to opportunities for sort of leveraging some stuff that they've done in what we're doing or vice versa.
This is the reason for coming and visiting.
Okay,
is that
perfect.
I feel like we've been sort of pursuing two parallel tracks really, and we definitely should make sure to leverage this stuff more. And especially, I don't know how familiar like government people are with the work that's been going on here. I imagine somewhat, but I think that's a place where.
Well, I've just sent his paper to 2 different governments.
Thanks. I owe you a beer. Thank you.
Does anyone have any questions?
Yeah.
Just to add on to what you said, Mike, I think now is also the right time to be more aggressive in publicizing because things have settled down. We now understand how to give C code to people that is really stable, robust. We're not going to rewrite the libraries a 3rd time. So we're really in a good place where we have more bandwidth to support like more widespread dissemination of the artifact. Yes.
Have you or anyone in your sphere done more work in the computational model as opposed to a symbolic model? And alternatively, would you like to rant about paper reviewers talking about a symbolic model?
I have found computational models to be quite difficult to explain and be productive with when you're not like a PhD in the area. Like the symbolic model speaks to me. I find it very intuitive to grasp. The computational one, I have written proofs in the computational model, so I can do it, but I don't find it very enjoyable. So I think that's perhaps why we have this extension of the computational model. There was that big line of work, the TLS implementation, that was doing a lot of game-based modeling, where the switches between a real world code and its ideal game-based modeling was done with an F-star, but the precise computational bounds were done on paper. And even that was really super, super difficult. So I think we kind of put it on pause on the basis that we did not at the time know how to be really productive and really good to compose these things and scale them up. It was brute forced, it worked, but if we were to redo it now, I think it would be very different. I would take a radically different approach. I would look at Squirrel, for instance, or any of these tools and be like, okay, how can we embed a little DSL that can do these games, and then like use meta-programming to compile the DSL to efficient code or something. Something along those lines.
Jonathan, if you click the bubble at the bottom, you've got 2 more questions.
Oh, thank you. Chat.
Yeah, or we can read it out. For you.
Oh, there's Scott. Okay. Engineer years. If we don't look at the tool chain, so not F-star itself, but just like the Hackle library, I would say 5 people full-time over 5 years, something like that, including like myself and Karthik and like various PhD students that came and went. Yeah, that's about that. How have you dealt with CI flakiness in your setup? Well, we think CI flakiness is great because it shows that you need to work on your proof. So it actually quite oftentimes happens that someone has a proof about, I don't know, a big tricky nonlinear arithmetic thing, and they're a rookie. They're like, yeah, my proof worked, great. I love verification. And they send it out to CI. And sure, it might work once, but the next day it breaks because of flakiness. And that is usually an indication that we need to get on the student's back and be like, hey, can you please fix your proof stat while it's still fresh in your head? And actually, it's great for shaking out like fragile proofs. We have found discrepancies between platforms on Z3, rogue SMT patterns this way. It's always unpleasant to debug these things, but in the long run, that's how you get to a stage where everyone is happy and your CI is not breaking under your feet regularly. With that being said, one thing we have to do, and that we oftentimes do, is what we call hints. Z3 has a feature where it will output the minimal set of predicates that it needs in order to derive a contradiction. It calls that an unsat core, and it can dump it to the disk and reload it. And that has proved invaluable to smooth out differences between platforms, because it's just too much when you have something that works super snappily on one platform and the other person who's on Windows cannot reproduce your proof. So for that, we use those hint features. And they're also like under CI and regenerated by CI on a regular basis, so that they're always up to date. Any other questions?
Very cool. Well, thanks so much. And I'm going to go out, me and Jonathan are going to go out for dinner later. If anyone wants to come with us, you're more than welcome. And Jonathan's going to be around all day. And I'm sure if anyone who's online wants to make the connection, I'm more than happy to introduce you. But I mean, I'm sure people can just email you directly as well.
Yep. I'm happy to take emails and to do informal chit chats, online or at the next conference.
Okay. Wonderful. Thanks a lot.